Matt, I make you a presenter and hope that works.
Seems to.
There we go.
All right. Thank you, Lucas, for the nice introduction, and good afternoon or good morning, wherever you are, everyone. My name is Matthew Lacey, and I'll just briefly apologize for the condition of my voice. I lost it yesterday evening, so I hope that it will hold out for the next 10 or so minutes for the first part of this. So as Lucas briefly mentioned, I currently work at Scania in the Materials Technology Department. I've worked at Scania for close to 4 years, and before that I was working in academia. I did my degree and PhD at Southampton. I finished my PhD in 2012 working on lithium-ion microbatteries. And then I moved to Sweden, where I studied lithium-sulfur batteries for the best part of 6.5 years. And today at Scania, I work a lot with cell materials analysis and research into new chemistries. And I will just also preface this presentation by saying that the contents of this presentation are my own personal views and should not be construed as the opinions of Scania as an organization. So I will just, there we go. Slide change works. I'll just get the ball rolling here with a brief look at the gap between what we can get in theory versus what we can engineer in reality with some simplified examples. So on this slide, we have an overview of what we currently have in terms of state-of-the-art battery cells in terms of energy density, just one of many key performance indicators or KPIs that we have for batteries. I think, as most of us who are working with batteries appreciate, the lithium-ion or lithium-based battery is not one chemistry as such, but it's a family of related chemistries. And energy density is just one important factor, but there are, of course, a lot of different KPIs that determines a battery's suitability for a given application. And there is just as much variation for these metrics among the different chemistries as there is for the energy density. So we have, for example, the NMC batteries, which is the higher energy version of what we have deployed in a lot of EVs today and related chemistries. And then we have slightly lower energy density batteries such as LFP and then LTO anode, which have different compensating KPIs which are better in other respects. So, for example, power capability and lifetime in the case of LTO anode. And energy density, I will focus a little bit on that metric for this presentation because it's something that you can fairly easily understand and also fairly easily calculate when it comes to theory and also sort of expected practical performance as well. But of course, for an application, we have to consider power capability, efficiency, both energy and coulombic efficiency, lifetime, both calendar and cycle life, the cost, the operating conditions, the safety at the system level is very important, the overall cost, including end of life, and then also increasingly important are the such as CO2 emissions and other environmental factors associated with the production. And batteries, of course, very complex devices, and each component, not just the active materials, will influence the KPI, each KPI in some form or another. And then, of course, there are other considerations, such as the manufacturing and the supply chain, which Ulrico and James will go into a little bit more later. Change the slide again. Hope it works. All right. So I'll start off a little bit with an exercise. What is wrong with these sentences that you see on the screen? So earlier in my academic career, as I mentioned, I worked with lithium sulfur and also briefly lithium air batteries. And I would read a lot of papers and I would routinely read sentences like these ones, such as which would introduce the battery chemistry and why it's interesting. So for lithium sulfur and lithium air, these are two chemistries which we really pursue because of their theoretical energy density, which is very, very high. So you'd often read sentences introducing the battery like lithium sulfur has a high theoretical energy density, such as for like 2600 watt hours per kilogram, which is much higher than lithium ion batteries of the order of 300 watt hours per kilogram, and things of that nature. And I should also say that these examples here are relatively recent papers, just from the last couple of years, and it took me about 90 seconds to find them on Google Scholar. So I take it that this is still a pretty common occurrence in these fields and probably others besides. Hopefully, you may be seeing the problem, but if you're not, I'll tell you. In each of these cases, there is a direct comparison or a implied comparison between the theoretical energy density on the materials level, so just considering the materials and not any of the other components that you need to actually make a battery, based on theory for the new system with what is already developed and deployed for the incumbent lithium-ion technology. So it's a comparison of theory to cell level, and it should go without saying that this is an inappropriate comparison to make, because these are two different numbers and they tell you two different things, and they don't tell you on their own anything about the relative promise of the new technology versus the old one. And these theoretical numbers, these come from thermodynamic quantities. In both of these cases, they come from the Gibbs free energy change of the materials that are being produced, which you can just look up in a textbook, whereas the lithium-ion battery metric is what is measured on a cell level and is actually a real number of a real device measured in some way. So there are lots of steps to go from theory to cell, and then some further steps to go to pack level. And I'll illustrate this here with a comparison of the watt hours per liter of a representative technology and the various steps involved to go from theory to pack. And I choose watt hours per liter here simply because it illustrates the point pretty clearly. So if I take this example, it doesn't correspond to any particular system, but it is roughly what you get for a state-of-the-art pack based on NCA cathode, graphite with silicon oxide in the anode, small cylindrical cells in a fairly conventional pack. You can probably imagine the kind of pack that I had in mind when I came up with this example. So if I calculate the theoretical energy density based on the maximum capacity that these materials could provide, and only the materials themselves, no binders, no current collectors, no cell can or anything, I get 2390 watt hours per liter, which sounds pretty good. That's pretty high. If I go the first step to what I call the reversible state. So the reversible is, we're still only considering the active materials, but it's considering what energy is can be extracted and then the reaction reversed. That is to recharge the battery over and over again. So in the case of NCA, we cannot extract all of the lithium out of the material because it's not reversible. And we have various losses from other places, such as silicon oxide. You can't use all of the silicon capacity and so on. So if we consider those, that number drops to 1865 watt hours per liter. Then to go to cell level, we have to take those active materials, we have to make them porous, which loses active volume. We have empty space. We need to have an electrolyte, we need to have a separator, we need to have current collectors, we need to have packaging for the cell and so on. And then that number comes down significantly to about 675 watt hours per liter. That's pretty good for cell level if you were to look at the previous figure again. And then to go to pack level, we have some more losses. We have to take those cells, we have to arrange them into a pack with some additional supporting components, such as the battery management system, the cooling system, electrical contacts between the cells, crash protection, whatever. And then that brings that number down to something like 270, in that neighborhood anyway. So it's quite a big difference. It's actually almost a factor of 10 difference between theory and system level in this case. That's quite a lot. And I have heard a few times in the past, in various conversations, presentations, whatever, related to new battery chemistry, so using rules of thumb developed from the experience of already developed technology. So, for example, I could derive a rule of thumb on this. I could say, like, oh, if you divide the theoretical energy density by the theoretical watt-hours per liter by 9, you get roughly what you should expect on system level. I've heard also before, divide the theoretical watt-hours per kilogram by 4, and you get roughly what you should expect on cell level. And this could be somewhat helpful, but I don't think it is. And in our article, this has been illustrated with this comparison. So in this comparison, we have two state-of-the-art but rather different system concepts, which are pretty current at the moment. So we've got one based on small cylindrical cells, the example I've already shown you on the previous slide, such as from a Tesla car. And then you have a rather different concept, such as that based on large format prismatic cells based on LFP in a cell to pack configuration, such as those which BYD is putting into their cars now. And these systems have a fairly comparable, not exactly the same, but fairly comparable system level energy density, both in terms of watt-hours per liter and watt-hours per kilogram. But theoretically, the LFP systems and the NCA systems are very different in terms of energy density. The LFP system, as you can see from the figure on the right, has maybe half the theoretical energy density in terms of watt-hours per kilogram and watt-hours per liter compared to the NCA version. But it manages to close the gap on the NCA system in terms of energy density in two ways. One is that the LFP material is more reversible than NCA. You can use nearly all of the lithium with no loss, with very little loss from the theoretical case. And more significantly, the pack is more volume and weight efficient because of the cell to pack configuration. So those two things mean that even though you start out with a theoretically inferior material in terms of energy density, you end up with a system level which gives you very similar performance. And then if you were to go, I think from this example, you should see that if you were to go to a different chemistry, lithium sulfur or lithium oxygen or whatever, it's very different chemistry, different materials, and these rules of thumb, if you apply them, will not necessarily be helpful because the limitations are different. So I will close out my part of this presentation with a little bit of food for thought. So first, inappropriate comparisons of apples to oranges, such as those which I showed earlier with theory versus cell level metrics. They're very, very common, and they should be avoided in when writing introductions to papers. And if you as a reader are looking at a paper on a new battery chemistry, you should look out for these in case they mislead you, because they are very common. I don't think this is done deliberately. I think it is mostly done accidentally, but it does happen. The second is that extrapolating from one scale, such as cell to pack or theory to cell, using the experience of one chemistry or something similar is tempting, but it will be misleading if the fundamental bottlenecks change. So that can be the reversibility of the material. It could be the thermal stability of the material, which determines how you can use the materials or the cells. If those bottlenecks change, you will be misled if you just apply the same thinking to extrapolate. And one of the takeaways of our articles is that manufacturers quite recently have exploited the better thermal stability of LFP to produce very highly volume efficient packs. And this has enabled energy density improvements without much innovation in the underlying chemistry. And this is worth noting, I think, because historically the battery field has been quite chemistry driven, and a lot of the research has been focused on developing new battery chemistries. But some of the most significant developments have been on the engineering side in recent years. And then lastly, up to now, the automotive industry in particular, I think, has largely sought energy density improvement by chasing these new generation chemistries, such as silicon anodes, solid state, and so on. Although market introduction of these chemistries is not expected until later this decade. Meanwhile, very large, or the biggest improvements in energy density have come instead from pack level engineering and primarily from China. So that's all I had to say about this, and I'll be checking in the Q&A if you have any questions from me. But for now, thank you for listening.
And
awesome. Thank you, Matt. I just needed my mouse back. Great. I think a very, very interesting thoughts, especially comparing the pack level performance of LFP and NMC. Is really, really interesting to see that the LFP can hold up with the NMC on pack level. So good food for thought. Let's move on to the next session with Ulrico. I hope the mouse works for you now, Ulrico, the flipping of the slides. Let me know if it does.
Yeah, seems to be working.
Perfect.
Thank you, Lucas. And I think thank you to Matt as well for setting up the scene so well for the following part. So myself and Ulrico, I'm working now as advisor for Sphere Energy. And similarly to Matt and James, my career has been in a number of different chemistries, and I've always been between lab and let's say industrial innovation. So my next part will be looking more at how what is the mechanism to get an innovation from the lab to the market, if you want. And this with this, I'd like also to try to address also that point about how, like, why there is this mismatch between theoretical values, between what's communicating, what's real. I think where I want to start today is really about discussing the different scales of where innovation happens, where it starts and where it ends. So when we think about moving a battery technology from the lab to the market, one reason why this is so complex, why there are so many opportunities for miscommunication, is that it's a very long process. It's a very complex process. So what you can see from this slide, which is again extracted from our paper, innovation is usually started in a research lab. So in a very controlled environment where we work on a very small scale. So here we present the technology readiness level, which are essentially a scale that is used to assess the maturity of a technology. And the idea is that when you're in the lab, you're doing high-risk research. So the capital you need to complete a project, for example, is relatively small. You can see here on the right an idea of the scale. And so is small the scale of the items you are producing. So a coin cell, which is a very common format used to maybe do screening of new materials, is very, very different from what's commercially available. And this ties with what Matt was showing earlier in his slides and the charts. Essentially, as we move down, you can see that the capital required to complete a project is increasing. This is reflected in a move towards manufacturing. So we start to need to test and manufacture larger cells, as you can see, for example, in a pilot plant. And then for vehicle approval, which is the focus of this chart, you need to start mass manufacturing. And that's where the real pain begins, I would say. And we had a lot of demonstrations of this, I think, in news and historically. So really, the point here is that people work at very different scales. So when we see these breakthroughs, these announcements trying to sell new technologies, it's very often coming from here, from research labs. And one reason why we think there is this miscommunication and misalignment is that there is quite poor communication between the two worlds. And I think as a battery scientist, having worked in different areas, I can say that nobody has really a good understanding of everything involved into a battery system. So you have specialists, maybe engineers who are capable of doing specifically a few parts. You have maybe engineers who are more expert on the system level, engineering level, or maybe materials level. So it's really, really hard to have somebody with that expertise and understanding of each step, because again, these are very, very different, but each one of those is required. And the key point is about moving up in scale. So we have been using this slide a few times now, and it's our second poll for today. So one thing that is very common, I think, is it's very hard to imagine like scale of where you're working at, what it means to scale up a product. Like in this case, we compared these two items. So one coin cell, which, as I was telling you earlier, is the typical size you do in the lab, and then 175 kilowatt hour Tesla 3-pack. So I asked this question already quite a few times, and I want to probe and ask you what you think is the different size, essentially. So we will be launching a poll now, and what we want to understand from you is how much cathode is contained in a coin cell compared to a pack. So I think Lucas has already launched the poll, so you can answer. And again, if you already answered this question or seen the answer, I mean, you can add it, but I would ask not to do it so you don't skew the statistics, because we've been thinking to run this a couple of times. Let's see how many times people get it wrong. I got it wrong maybe the first time, like when I was preparing this quiz, to be honest, because it's really, really hard even for me, and I think for everybody to really even imagine the difference in size. So we have about 100 people who have answered the question. You can take maybe another extra 30 seconds, then we need to move on.
So let me share the results.
Yes, thank you, Lucas. And
so most expected 160x. Federico, I hand over to you again.
Thank you. And yeah, as you can see from the results, it's really, really hard to imagine the scale. So what we do in the lab is millions of times smaller than what is required in a real battery pack. So you can imagine that it is just one component, and again, it's really different way of thinking. You need to consider really the very different variables. And here you can read a little bit more about really these numbers. I think these are really, really important. So what we wanted to point out here is that the orders of magnitudes are really, really different. So one 10 gigawatt hours per year battery pack manufacturing would produce probably enough 130,000 Tesla 3s, and this would require about 14,000 tons of cathode active material, more correctly positive active material. And again, to give you a bit more scale, the Umicore European cathode manufacturing plant produces enough material for 40 gigawatt hours. So you can make very easily the maths here. So there's this problem of scale and working at different scales, and that's where we think there is a mismatch. So one of the key points, and James will be diving a bit deeper on this part, is that supply chains and market is very, very complex. So this one representation of the circular value chain for batteries, that's how we think we should be looking at it. And again, this overly simplified, so we couldn't include all the component steps that are required for manufacturing a battery pack. But what you can see here from this chart is that we have many different steps. And each one of those is characterized by very different industries. That's what I was telling you a little bit earlier in the beginning of my part. So we have mining, refining, active material manufacturing. These are maybe, the first one is of course very upstream. It deals with the extraction. Then we have chemical industry, and then we move to cell manufacturing, which is more related with high precision manufacturing. And as we move on, we have different parts, different components. We have recycling, reuse. So the skills needed to get a battery in the market and bring it from beginning to end of life, again, is very, very different. There is, I think, no industry which can take it all yet on its own shoulders, and that's for good reasons. And this is reflected also in a very different time to market. So starting here, we look at how long it's likely to take to get one project, for example, from investment, so from CapEx, capital expenditure, to start. And each step is very different. It's very hard to know before how long it will take to take up technology just from when we put the money in to when it's reaching the market. So you can imagine that when it's about innovating, from moving not from capital expenditure to project start, but from the lab to market exploitation, it can be much, much longer. So, and it's probably going to be extremely hard to forecast. So it's easy to, if you want, give wrong or right information. There is no, most probably there will be such a high degree of uncertainty that it will be really hard to really give a definite answer. And again, to stress more this aspect that there is a lot of uncertainty, and also pitching one of our next white papers that we're going to publish. When we look for example, at solid-state batteries, and I work on this technology for really many years in academia and industry. Here we are trying to look at the different players, and we present this pyramid, if you want, this tracker for solid-state battery innovation. And we show also some of the typical lens. And you can see, for example, being in a research lab, when can we move to pilot status on the left? There is a huge degree of uncertainty. And what's also showing, and it's this risk aspect I was mentioning at the beginning, is that not everybody will manage to climb the tower. So very few will reach startup production, SOP, conventionally said. So particularly for solid state, I won't be spending too much time on this particular slide, but we have really a wealth of very different technologies. So with this terminology of solid state, we probably include 10, 20 different cell chemistry, and each one characterized probably by a slightly different value chain, what I was telling you before. So having a thorough, comprehensive assessment of these technologies is really, really complex. And that's why there is a lot of space for miscommunication, essentially. And here I'd like to conclude my part, just to give you enough time also to James and Lucas to present, and happy to take any questions. And yeah, James, up to you.
Thank you, Ulrico. Thanks a lot. And yeah, you have seen a sneak peek of the new white paper that's coming out soon on the solid state aspect of things. So stay tuned here. I forgot to mention, if you have questions, just shoot them in the Q&A. We will take them at the very end, and we're also recording the session and provide you with the deck afterwards. So no need to take screenshots here. All right, with that, James, I hand over to you. I hope the slide moving works.
Perfect, thanks, Lucas. And thanks, Ulrico and Matt, for kind of building up the background here. So I'm going to be talking about why it's important to understand markets. And I think one of the kind of key messages of the paper was that there needs to be more communication between academia and industry. And this is something that Ulrico mentioned as well, and Matt. But really kind of when I say understanding markets, it goes beyond just kind of collaboration between industry and academia. It's actually the entire ecosystem that needs to be working together. And as academics or industry, you need to be aware of what's going on across the ecosystem. But back to that kind of key message about industry and academia kind of talking and really industry guiding academia, because in fact, that does happen to an extent today. And the obvious example there is with technology roadmap. So here we have a technology roadmap from CATL. Now, if I was a new researcher coming into the battery field and I was thinking, okay, what should I start looking at? I could look at this roadmap and say, okay, based on where CATL wants to go, looking at high nickel cathodes or kind of new anode materials like silicon or lithium metal is probably going to be a suitable line of research. And that's where I should kind of turn my focus to. But in actual fact, when we see product roadmaps like this, it doesn't tell us the whole story. In fact, it's only telling us one thing when we really look at this, or perhaps two, and that is what industry wants to do with energy density. The other kind of consideration is there is some information there on potential materials that can be looked at, but those are just materials that are kind of filling in that need for higher energy density. Now, while that is useful in itself and it gives the direction that the market is wanting to go into, it really doesn't tell you the reasons behind that need for higher energy density. So when we're looking at technology development and trying to understand what it is the market wants and what researchers should be looking into, it's actually better to link these kind of key metrics to performance indicators. So when we talk about gravimetric energy density, we're actually talking about driving range, charging requirements, cost, safety, impact of subsidies. When we're talking about the kind of safety or the thermal runaway temperature, we're talking about safety performance, operating temperatures, thermal management requirements at the pack level. You know, similarly, cycle life, it's not just how long does this system cycle for, it's actually going to be very application dependent. If you have an application that requires high cycle lives, what you're trying to optimize for is probably going to be the total cost of ownership. Indeed, it also kind of feeds into things like the life cycle assessment. So when we talk about metrics and the industry guiding academia, it goes beyond just saying, these are the performance metrics that we want. We really need to be thinking, what are the end device kind of KPIs that are needed? What do systems need to be able to do for these technologies to be adopted in a certain application? And I think that's really something that we're missing today. So there generally needs to be more of a kind of collaboration between academia and industry on this front, but it needs to go beyond the kind of technology roadmaps that we have out there today. And the thing that I would add to this is that while companies are continuously looking to adopt technologies that have ever increasing performance, we should always remember, particularly as academic researchers, that one of the most important things is, even when a company tells you it's not about the money, it's always about the money. People are not going to adopt a new technology that has a significantly higher cost basis unless it has a clear cost down trajectory that gets it to close to or at parity with the incumbent technology. Similarly, there are some examples where perhaps people will be willing to adopt technologies that have a slightly higher performance but come at a higher cost, but those tend to be niche markets with lower volumes. So examples of that would be the defense industry, where price really isn't a problem, but performance such as energy density, can be. Similarly, if you look into the consumer electronics markets, again, price on a per kilowatt hour basis doesn't tend to be such a big factor there, because you have a few watt hours going into your cells. But if you're looking at it from an energy density point of view, actually the volumetric energy density can become a really important factor. So you may find consumer electronics developers willing to pay higher prices for higher volumetric energy density systems, because it means they can get more watt hours into the kind of given space of your consumer electronic device. So I think that's something that, particularly at the academic level, is very hard to do because you don't have the appreciation of the supply chain. It's hard to forecast economies of scale that will come as you move along that TRL scale that Ulrike discussed earlier. But it's something that we should always bear in mind. And examples of this are if you develop a new anode material, for example, that has a very high cost or raw material that has very limited supply basis, that's unlikely to ever make it to commercialization. So when we're thinking about these research projects, particularly at the lower TRL levels, we really need to be thinking forward and understanding whether the supply chains or the kind of cost down trajectories will actually support the adoption of these new technologies. Now, kind of continuing along with this kind of thinking along kind of technology roadmaps and industry guiding academia, I'm going to slightly change tacks and start talking about kind of chemistries, but using a specific example of China and in particular Chinese EV subsidies. So those of you that are familiar with the EV market in China will know that the subsidy regime that was introduced in 2015-16 was one of the largest drivers behind the kind of success of the Chinese EV industry. Now in 2017, they changed the subsidy regime and they linked it to not only vehicle range, but also battery pack energy density and the size of the battery pack in a vehicle. So depending where you fell along those metrics, you'd get different subsidy multipliers. So you can see here that in 2017, if you had a battery pack with more than 160 watt-hours per kilogram energy density, you would get a subsidy multiplier of 110%, which means you get 10% over the kind of maximum subsidy, as it were. In 2018, the Chinese government changed that, and so you actually got a higher subsidy for the higher energy density systems. Now, this is kind of seen as one of the factors that drove the adoption of chemistries like NMC 811 in China, combined with other kind of factors, macro factors, such as high cobalt prices. But you can see that actually the impact of the Chinese subsidies had a big effect on the Chinese battery market and EV market. Now, if we fast forward a year to 2019, there was another big change. And the kind of main change that you can see here is, well, at the top end of that, at that 160 watt-hour per kilogram level, the maximum subsidy has been reduced from 120% down to 100%. And at the bottom end, now battery packs that had energy densities up to 120 watt-hours per kilogram would no longer receive a subsidy. That probably doesn't seem like that big of a deal when you kind of look at it abstractly. But actually, if you start to consider that at the time, the energy density of commercial LFP packs in 2019 was around 120 watt-hours per kilogram at the maximum, you realize that suddenly the change in the subsidy regime means that passenger electric vehicles with LFP packs would no longer get any subsidy. And the effect of this was that on a dollar basis, battery packs of the same size, kind of LFP and NMC, actually the NMC battery pack, if you had 160 watt-hours per kilogram energy density, which is similar to kind of NMC 811 at the time, your battery pack would be cheaper to the consumer using NMC 811 than using LFP. Now, that in itself is quite interesting, and you would imagine that the impact of that is that more automakers would adopt NMC-based batteries. But what's interesting is if you look at the kind of theoretical maximum energy density that could be achieved with LFP packs at the time, you can see that you could push it from about 120 watt-hours per kilogram up to a little over 140 watt-hours per kilogram. Now, if manufacturers could do that, they would suddenly be able to receive some subsidy for the LFP packs, somewhere around kind of 80%. And now what you find is that your LFP packs at 140 watt-hours per kilogram are going to be cheaper on a dollar basis for the same pack size as an NMC 811 pack. So suddenly, what the battery manufacturers in China realized that they could do is that they could slightly tweak the pack design to get a higher volumetric packing and a higher gravimetric energy density in the kind of cell to pack design. So the Blade battery introduced by BYD and similarly kind of cell-to-pack designs by CATL. So this is a really interesting kind of pivot, because suddenly manufacturers were no longer just looking at energy density and going to better materials. They were looking at the entire system design and seeing how they could optimize it for cost. And as I'm sure most people will be kind of aware of, as a result of that change at the pack level, we now have a situation where over 50% of battery packs going into passenger EVs in China in 2022 on a gigawatt hour basis were LFP. And that's a kind of complete turnaround from the industry. In 2018, it looked like LFP would be almost completely phased out of passenger EVs. But by kind of thinking beyond the kind of typical roadmap and thinking about systems holistically, we see that the manufacturers managed to come up with a neat solution that actually ends up with better kind of supply chain utilization, lower cost to the consumer, and a reasonable performance, and is now something that's being copied around the world. So I think this is really kind of, from my view, a clear example that wherever we are within the industry, whether we're in academia or working on commercial products, it's not enough to just look at the kind of general direction that the industry has been moving in the past and say, okay, this is what I'm going to follow. You need to look at everything from supply chains, government policies, subsidies that are available, and the needs of your customers and end users to develop systems that are geared towards making the EV industry kind of more accessible. And you don't necessarily have to do that with the most high-tech technology out there. I'm going to leave it there and pass it back to Lucas now. But hopefully you found this interesting, and as always, put any questions that you have into the chat and I'll get to them in a second. Thank you.
Awesome. Thanks a lot, James. Very, very nice summary. And I really love the point that new is not always better. And especially when we look at the LFP chemistry, it's kind of a revival now, competing very heavily with the NMC. So let me just summarize what we have heard today a little bit. We have been talking about very many different factors and why this technology is so complex. We have a lot of innovative materials. We have the old materials that are in the market that are having a revival due to engineering aspects. We have a lot of new manufacturers competing, especially in Europe and US now, all these gigafactories coming up, which is causing a lot of stress on the supply chains, whom to trust, whom to partner with, the second big factor. And then obviously all of us having massive expectations, right? The scientific journals wanting to see high performances, very good values. Society wants to have the battery being green overnight, and also industrials, right? They want always pushing on performance, pushing on cost, pushing on sustainability topics. And I think what also became clear when going through all the three sessions is that we're really lacking a little bit a standardized approach on how to look at things. Matt pointed it out in the beginning, Ulriko and James grabbed that point as well. And I truly believe, and we at Sphere believe, that this standardized data is one key to drive this technology forward and kind of overcome this mix of hype and confusion that's going on right now in the market. And actually, I want to conclude this session just with 3 steps, which we think at Sphere are suitable to approach this market. And the first one really starts with the mindset. Kind of a no-brainer, but also kind of not. I mean, having realistic expectations is probably the first thing we should go with, and reading all these newspaper articles where there's another silver bullet or another breakthrough is simply not going to make it, right? It's a very challenging topic. It's has a lot of physical limitations, physical and chemical limitations that we need to understand when judging a performance of a battery technology properly. And that's especially what Matt pointed out in the beginning. And I think we simply have to embrace that this technology is complex. Battery is a freaking complex technology from a science perspective, but also from an engineering perspective. Point 2 that I wanted to mention is the trade-offs. As soon as you read higher performance, think about what it has on the other side. It's always a trade-off. There is no silver bullet, as I mentioned already, right? When you have a higher performance, you usually have more aggressive or more reactive materials in your battery. You may have higher energy density in your battery, which triggers more reactions. So there is always a kind of trade-off when it comes to higher performance, usually related to cost, cycle life, safety, or sustainability when looking at the cobalt, for example. And what is important here, especially when we move to these more hype technologies like silicon-rich or solid-state batteries, there is a need for new ways to measure these kind of things, especially when you think about high silicon content anodes. You need to understand the swelling. There is a lot of volume expansion in there. You need to think about new ways to mitigate the heat dissipation, for example, and you need to look at software and data to understand the measured data better, to maybe come up with new ways to understand aging and degradation mechanisms, to really fully unravel or have a clear view on these trade-offs and not just blindly follow the marketing messages here. And as a third point, I think it's very important to have a comprehensive view on a performance of a battery technology. I don't want to go into each of these parameters. We're also going to share these slides later on, so you need to take screenshots. But I think it's really important to understand the performance parameters and all the other trade-offs like cost, cycle life, sustainability, and safety, obviously. And not only understanding these parameters, but also putting them into context. And I just made this here exemplary for three different areas or three different markets: the electric vehicle market, which is obviously the biggest one, the stationary market, and the power tool market, which all have different expectations and different requirements. And as we have seen today, there is many different battery technologies. There won't be a one-fits-all solution. There will be solutions for all the different applications. And I think this is also where we have to judge the individual technologies properly. Potentially a very high costly NMC technology that has super performance parameters will never make it into a grid storage application. So it's really, you need to understand where the application of such a battery lies and understand the full trade-off between performance, cost, safety, and cycle life. And with that, we come to the end of this session. I just wanted to point out really quick what we do at Sphere to support this field advancing. We work mainly on three areas. We support the R&D side with standardized test equipment, where we really try to help researchers on the lab scale, gathering standardized data and helping basically from the bottom up to get some kind of standard into the field of publications. And also the communication with industry that we heard a couple of times today as well. Here we offer standardized test and technology validation services here out of our test center where I'm sitting right now. And to combine this, we truly believe that the battery has a profound impact also on the organizational level of a company. We're working here on a model called battery-driven organization, because we believe that the battery should be at the core of companies that implement batteries into their products. And it has a profound impact on strategy, on team, on compliance, regulations, and to capture all this and help people advance with batteries in their products. That's what we do in our third work stream. So now let me close that session and switch over to Q&A. Well, Rico, I don't know if you had the chance to look at the sessions.
Yeah, I did look at a few questions. I think maybe we can try to put them together. I saw there was a lot of, I tried to answer, I think all of us have been trying to answer you in the chat box because we have a lot. Maybe we can start with one about general trends about sodium ion. So we pack a few of those together because I saw quite a few people were asking about general like ideas. When are sodium ion coming? Like who's winning the race if they can replace lithium ion and things like that. So I can start maybe by answering this, give my personal opinion, and then pass to Matt and James. So in my opinion, sodium ion are very promising. They're probably going to reach market exploitation. It's quite realistic considering all the announcements that we're seeing today and all the companies that are working on this technology, not only here, but also in China, which I consider our model market, which is the most advanced in my opinion. My opinion on sodium is that they will never be fully competitive with lithium-based batteries because thermodynamically they just cannot get there. So if you remember Matt's chart, the first point theory is a bit lower than lithium ion, and I don't see why they should be much better than lithium ion. So in a few applications they might be very competitive, particularly for price, if the supply chain develops, and then, as James was saying, you know, they reach that point where they're more price competitive. But my opinion is that they will have sort of smaller market, like a smaller niche, maybe 10-20% in the long term. But in the beginning, like you never have a technology immediately replacing another one. It always takes many years before, you know, we can move maybe from lithium ion cells to a sodium ion cell because of the length of the validation process, because we need to get used to it. So it would still be a long time. I don't know, Matt, James, if you want to add something here.
I would even suggest, Ulriko, to maybe have 13 open more questions, and maybe there is we're also working on a point of view on the sodium ion side, so we'll publish that in a couple of weeks, so there will be more insight there. Maybe another question about fabrication methods. I find that quite interesting. I mean, we hear a lot about freestanding electrodes, electrospun electrodes, 3D electrodes. My personal point of view here is that it's clearly a cost game, and you have to consider as well the already spent money in gigafactories and in fabrication processes, right? So if you have a process that it gains you some efficiency in the production, but costs a lot of money to implement or change even a fabrication line, I think it's rather unrealistic to have these implemented, because I think once you have a gigafactory up and running, it's all about being more efficient and being better in producing what you have already, rather than changing the production process all the time and keeping the investment going, basically. Maybe an interesting one, Matt and James, for you. Do you have ideas of how to incentivize the industry, make open source their data to help academia not just focus on real life problems, but also help the field to advance faster? So what is your opinion on open source industry data?
It's a good question and a tricky one. I think we discussed this quite a lot while we were writing the article, is that a challenge, of course, with working with industry is the requirement often to keep certain things confidential. And that's not something that the engineers working on problems and collaborating with academic researchers necessarily have control over. I suppose that the best we can do as a start is to sort of collaborate openly and transparently as best we can, and take advantage of whatever opportunities there are to be to work transparently and share insight and knowledge, and I guess do what you can to sort of help convince your managers or the company that at least to some extent there is nothing to be afraid of with working transparently and sharing some things, at least. I mean, there's always going to be a requirement for keeping certain things confidential, but I think when you're working with fundamental problems, there are certain things you will be able to share and can support academia in solving a common problem.
Great.
I hope so. Anyway,
I think I just add to that. I think we are beginning to see kind of more industrial collaboration between academia and industry. And, I think there's a number of these kind of projects going on in the UK now, where you have industrial partners alongside kind of academic institutions. And it's been going on for a while, but we're beginning to see it kind of ramping up in the battery industry. And I think that those are kind of key touch points that can really help academia to understand the kind of needs of industry. And it's kind of similar when you go beyond academia to the kind of startup space. Actually, kind of startups still tend to not have a kind of idea of what the end performance needs to be. And so in order to kind of meet that, what we typically see is startups need to have joint development agreements with industrial kind of players who understand end device performance and can kind of guide the startup on exactly what needs to be done. So, I think it's probably one of those things that will occur more kind of organically over time. But there's certainly kind of a lack of that at the moment. And I think it only grows organically over time if we continue to make this point that you need to have more kind of collaboration between academia and industry.
Absolutely, James. And I think that pretty much relates also to the question of Peter, who's asking what are the real or realistic things that can slow down or speed up the development cycle. And I fully agree that one is absolutely the collaboration between academia and industry. And I think a second part that is very much underestimated, besides the IRA and the Green Deal money, kind of helicopter money that's coming there, is the talent. Right, I think a lot of these new projects that are going up now everywhere, the Gigafactory projects and the likes, struggle in finding the right talent. And I think this is something where we all need to support each other, educate people, trying to bring people to the field. I think it's a tremendous push right now. I think Matt was telling me that they have over 140 applicants before in the university for a PhD position. So it's amazing to see that there is a trend towards this topic of electrochemistry. But I truly believe that besides the money, it's really the talent that we need to build up to speed things up here. I don't know if you want to comment as well, Ulriko, Matt, and James.
I think, I think one of the things that's worth kind of commenting on, and this is I suppose maybe more on the kind of adoption side of things rather than technology development, but certainly within OEMs, and I think this is fairly well understood, but within kind of particularly Western OEMs, the mindset is still kind of linked to, let's say, internal combustion engine vehicle development times, where you're looking at kind of 5-6 year periods for developing new models, and maybe 3 years for kind of doing model refreshes. Whereas kind of battery technology is moving at a far faster rate. And so we see in Chinese OEMs that they are much better at quickly kind of developing products and integrating them into their vehicles. The example here, again, being BYD's Blade battery, which was developed in about kind of 12 to 18 months in response to, or partially in response to kind of changes to the subsidy regime. So organizations themselves need to be more nimble if they want to stay at the forefront of the kind of technology development. And I think that's probably a slightly kind of harder ask for these big companies to change their mindset. But then at the same time, I think that's also why we are seeing in some instances the battery development divisions being slightly separated from the kind of main OEM. So PowerCo and VW being an example of that.
Awesome. Great point, James. And with that, I think just looking at the time, we're slightly over time, but appreciating so many people staying with us. Big thanks to Ulriko, Matt, and James again for having this session today with me. I hope to see you soon all again. We will keep you posted. Stay connected to our LinkedIn channel, and have a great weekend when it's time. Thanks a lot, guys.